We are now starting chapter 2, which is first order differential equation. So in this chapter, we will learn how to solve first order differential equations. Different methods will be explained. One method you have already seen in the previous chapter, which was the separation of variables. And not every equation can be solved by that method, so we'll need to see other methods. Also, in section 2.1, it is just an introduction section, so there are no questions no exercise at the end of this section, but we want to be introduced with some special kinds of equations, first order equations, which are derived from real life problems. So here we are going to discuss the motion of a falling body, or motion of a free fall body. So the situation is that we have an object that falls through air toward Earth. Now remember, if something can be coming from up there, or some can be thrown upwards and it eventually comes back. So assuming that the only forces acting on the object are gravity and air resistance, determine the velocity of the object as a function of time. So this is what we are, this is our real life problem. Now we are going to convert it into a mathematical model or a mathematical equation, and then we need to solve it to understand what the velocity will look like. So according to the Newton's law, second law of motion, we know that F is equal to ma, means the force on a body, falling body, is equal to its mass times acceleration. So acceleration in this case will be due to gravity. And acceleration also is the derivative of the velocity of the body. So we can write it as F is equal to m times dv by dt, where dv by dt is equal to a, the acceleration. Note here that the force will be directed downwards because the velocity is acting downwards. Now near the Earth's surface, the force of gravity is due to weight only. So weight is given by m times g, mass times the gravitational constant, or not the gravitational, sorry, acceleration due to gravity, which is denoted by little g. And the g is, if we are in the MKS system, the meter kilogram second system, it's called MKS, and then we unit the value of the g will be 9.8 meters per second square. And if we are in the foot-pound system, which is used in USA only now, the MKS is used in the whole world. So this is in foot-pound, the value is 32 feet per second square. Now, so we mentioned that there will be two forces acting on the object. One is the weight, and the second one will be the air resistance. So air resistance basically depends on the shape of the body, the material it is made of, and of course the velocity of the body. So at this moment we can just say that we can assume that the resistance is just proportional to the velocity, and so we can say that the force due to resistance is minus b times v, where b is a constant. Well, why is there a minus sign? Because the resistance we expect is going to act against the other force, which is the weight. So because it's going to stop or stop the motion towards the Earth. So we end up having an equation m dv by dt is equal to mg minus bv. So as I mentioned earlier, b will be known. B will be a known value because it's a constant, and it depends on the material of the object and the shape of the object. And little g is the acceleration due to gravity, and little m is the mass of the object. So now we can actually solve this. This is actually a linear differential equation in V. So in this case, it is a linear differential equation, linear first order DE. And in this case, the independent variable is equal to T, dependent variable is equal to V. And we want to find V, so we need to solve this differential equation. So we can do it by separation of variables. We see there is a V term here, so V is a variable, and we see a dV here. So we have to move the V term on the other side. Now, by adding and moving it to the left side is not going to help us, because we want dV to come, and with the V term. So the only way that we can, have some sense in the equation is that we move the whole quantity, which is over here, to the left side. So, and also we move the dt to the right, and along with it the m. So this is what I will get when I exchange these. So this quantity, so we have m dV by dt is equal to mg minus bv. So I'm first think about that we are going to divide by m and multiply by dt. So we get dt over m. So this goes from here, it went to the other side. Now on the left side we are left with dv only. So now we will be dividing by this term. So we end up getting this dv over mg minus b. So this is what we get on the left side. dv minus over mg minus bv is equal to dt over m. And now we put an integral sign on both sides, and we should be able to integrate this equation. Now right hand side is easy. It will be just 1 over mt plus a constant. But the left hand side, maybe some of you can solve it directly, but in easy ways to use the u substitution. So because now remember mgb, these are all numbers, so we can take u equal to this whole thing, mg minus bv. So then we, on the right hand side, we have m 1 over mt plus a constant. Excuse me. So now when we take u is equal to mg minus bv, then we have to find the du. So the derivative of mg will be 0, and minus bv will give me just minus b and then dv. So that our dv is looking like it is equal to negative 1 over b du. And then we substitute back for the dv this value that we just calculated, negative 1 over b du, and for the mg minus bv I replace it by u, and now it becomes integral. And b is a constant, so I took it out of the integral. So inside we are left with 1 over u du. Now this can be integrated as negative 1 over b ln of u. But u is mg minus bv, so we end up getting the integral on the left hand side is equal to negative 1 over b ln mg minus bv. Now right hand side, we said is going to be t over m, so now we can put the value of the integral on the left is equal to the value of the integral on the right plus the constant of integration. So now just we move this negative 1 over b, means we multiply the whole equation by negative 1 over b, and so that on the left side we are only left with the logarithmic term, so we isolate the logarithmic term, and the right hand side becomes minus bt over m minus bc. So now we can take, so we have mg minus bc minus bv, and there is an ln here, equal to minus bt over m or b over mt, however you want to read it, minus bc. So we want v, so we want to isolate v here. So v is hidden inside the logarithm over here, sitting here. So we cannot just pull it out directly. We have to do something. We have to basically get rid of this ln here. How do we do that? We think of it like two ways. We apply the conversion from logarithmic form to exponential form. Or you can say, sometimes students say that we are going to raise the both these sides to e, and then if you raise it to this side, then the ln and the e cancel out on the left hand side, and we get mg minus bv, and on the right hand side we have e to the minus b over mt minus bc. So why can we say that the ln and e cancel each other? Because there is a law of logarithm that if you have a raised to the power log base a of x, so if you have a number raised to the power log to the same base as the base you have here, and whatever is in front of the log term, that this quantity is equal to that. So if I have 10 raised to the power log of 5, my answer will be 5. Why? Because the base here is 10. When the no base is written, it means base is 10. So now this 10 is being raised to log base 10 of a number, so you get back that number. So in our case, if we have ln, so if you have ln of ln of x, well, you cannot throw away x here, but if you have ln of x is equal to p, so you can convert it into logarithmic form, exponential form, by saying base, which is over here, which is hidden. When you have ln, remember the base is e, so you can say e to the p is equal to x, or x is equal to e to the p. Or the raising to the power means if you have e raised to ln of x. Why e raised to ln of? Because remember, when we write ln, it means log base e. Then the answer will be x. So that's how we get mg minus bv on the left side, and on the right side I have this quantity. Now using the the exponent rules, I can split this and write it as e to the minus bt times e to the minus bc. So how did I do that? What rule did I use? So there is a rule that if you have x raised to the power m times x raised to the power n, you can write it as x to the m plus n. So now if you have x to the a plus b, you can write it as x to the a times x to the b. So that is what I used here, because this can be thought of as e to the minus b over mt plus negative bc. So I can write it as e to the negative k over mt times minus bc. So now I can split it as is given here. And now bc and b is a constant, c is a constant, so bc is a constant, so that e raised to the power minus bc is a constant. So now we give it a new name, uppercase k. That's what I have named it here, uppercase K, this one. And so that, and K is a constant, remember. So that the equation becomes, here, we can now write it as mg minus bv is equal to K times e to the K over mt. Because now this thing whole as a whole is not a constant, remember. Only this part of the expression is a constant. We keep it like this. We do not give it another name, although we could. So remember, now we have to get v by itself. So now the next steps shouldn't be that hard. So the first thing is we subtract mg from both sides. So left side is we have minus bv, and on the right side we have k e to the minus k over mt, and then we are getting the minus mg term from the left side. So next thing is we divide by negative b, and we end up getting this equation. So this is our v. This is the equation for v. But now consider an initial condition given, which is v of 0 is equal to v naught, and plug it in the equation for v, and we can find the value for k, which comes out to be mg minus bv sub 0 or bv naught. Now we go back, plug it in the equation, and we get v is equal to mg minus b plus v naught minus mg over b times e to the minus p over mt. So with this situation, what can you say will be the limiting velocity of the object? Limiting velocity of the object. So and when how will we find it? Well, if we draw some solution curves for this v, which is done down here, you can find where it is horizontal, the solution is horizontal, that will be the limiting velocity. Also, note here we can find the limiting velocity by taking the limit of v as t goes to infinity.
Michigan. There are currently no weather alerts.
Sorry about that. Okay, which means limit t goes to infinity of mg over b plus limit of t goes to infinity
it's about 5:38 and 14 seconds p.m.
v naught minus mg over b e to the minus b over mt. Now this is a constant, so the limit doesn't affect that. We get the same value back. But now when we look at the next term, this is a constant, so that will stay, but a limit will be applied to this, and limit as k goes to infinity of that quantity is 0, so that we end up getting just mg over b. And here is a sketch of some of the solutions. So note here the limiting velocity is mg over b as just found, and no matter what speed the object starts falling towards the earth, eventually it is going to gain the limiting speed, and the limiting speed is going to be mg over b. Okay, so this is what you have to remember, how we came up, or how we gathered the information, collected the information, and came up with the solution of the first. We came up with the differential equation for the velocity, and then we found the velocity. That's all for this section.